So we have now our swimmers, which can be controlled by light, shining just on the metal cap and heating it. And we need a setup to control them with a feedback control mechanism, and we need some kind of ideas of how to describe these processes and the accuracy of the control in any kind of way. And that's what I'm trying here in these three sections in this kind of chapter 2 on feedback control. And they are essentially about experiments we did, but there's not a whole lot of other experiments using feedback control so far, but there's a growing interest, and there are of course very nice applications also of the Beschinger group, which I will mention at the end of this lecture. So first of all, what's the experimental setup? That's the experimental setup at least we use, at least in a kind of sketchy version. You will see in your exercise a snapshot of that in more detail. So on one side, we need something to heat up the metal structures on our active particles. And for that purpose, we use a laser at 532 nanometers, so green. That laser has to be controlled in its position in the sample. So again, to repeat, the idea is to control each individual particle separately with the help of propulsion, and not the whole ensemble alone. So therefore, we also need to focus the laser on each individual particle separately in a different way, and must be able to do that. And that is achieved here in that setup by an acousto-optical deflector. So the acousto-optical deflector, which has two axes, works in principle with the help of acoustic waves, which are generating a grating, and that kind of grating is changing its grating constant with the frequency of the acoustic wave, and by that way you can achieve a deflection of the laser very, very quickly. And that is done here by this kind of AOD, which you see in the experimental setup later more clearly in your exercise. So that goes through a 4F system, and that 4F system is actually used to focus the laser here at a certain position in the sample plane through the objective lens we use. The objective lens is 100 times Olympus objective with a numerical aperture of 1.2, but which is close to 0.6 numerical aperture, because we use here from the top a dark field illumination. You see here that kind of image, which I come to in a second. The dark field illumination is done with a dark field condenser and an LED, a white light LED. And the dark field condenser is an oil immersion condenser, which has a numerical aperture of 1.2. So the light which comes through the dark field condenser is in a cone here, and that cone has an opening angle which corresponds to the numerical aperture, or the sign of the angle of that opening angle is the numerical aperture here at the end. So the collecting numerical aperture has to be smaller than this 1.2, and therefore we close the objective lens condenser here downstairs. The LED has some additional details. We use a flashing LED actually, which is on only for a millisecond or so. That helps us to control delays in our feedback loop in a certain way. This will not play a too important role, but once you really want to control it very accurately, this might be an option where you would like to have a look in. The light which is scattered is then imaged onto a CCD camera. In our case, this will be an intensified CCD camera which we use, which can do frame rates or exposure times from 10 milliseconds to whatever you want in principle. Most of the time we use here exposure times around 30 to 50 milliseconds for that camera, and that means after 50 milliseconds the next image will be taken. Right? The images are analyzed in our own developed software, which is first of all a modular LabVIEW program which we use, where you can add different modules for image recognition and things like that, and for the control of all of these devices here. And that LabVIEW program is also feeding a real-time board with the coordinates of all of the particles we detect, and that real-time board then finally controls the acousto-optic deflector. So the real-time board is doing its own job. It's not depending on Windows or whatever you use in any kind of way, and it can do that very fast. So it has some very fast analog digital, digital analog converters, and they are controlling the AOD here very quickly and steering the laser essentially autonomously. So there's the whole procedure works then in the following way for the feedback, at least, that you take some of the images of your particles, which could look, for example, like this here on the left side. You see actually a neat experiment the student has done once, rolling one of the Janus particles 1 micrometer over the surface of another and taking all of these images, and you see how the dark field images really represent the asymmetry. So here, this is the gold cap, this is the polystyrene cap, and you can determine the three-dimensional orientation out of that. In the case you have the symmetric swimmers, we can create really beautiful images of the particle, which we then analyze in real time during our measurement. So in many cases also, we do not really record movies anymore because it just takes so much space to have an image. You can just record the positions. So the image processing is done in LabVIEW, either with internal routines of LabVIEW, but if you have more complicated samples, of course, you would like to use more advanced techniques. For example, if you have different particles which have different brightness, different signal to noise ratio, different shapes, and you want to have classifications of the particles, you can use the deep learning modules, which you've probably either generated or one of the beautiful work here of Giovanni's group, published by Zaga, for example, here. You can use that for our real-time stuff. We use our own modules, which are, however, not as sophisticated as Giovanni's, of course. So from that, you get information, for example, on the position, the 3D orientation, the shape, the type, the size of the particle. You can get, in principle, any kind of information, and you can use that information to develop a particle-based rule in this feedback control, which leads then to a certain action. We see some simple examples in the application section, but this is the way it goes in principle. All right. So this is the feedback system, and we should have a look at some particular examples now that brings you to the limits of this feedback control. Okay, so the first one will be the photo nudging of a Janus particle. So the prototype of the active particles is, of course, the Janus particles, which has a symmetry axis which rotates by rotational diffusion and which propels, you have a propulsion of the particle in a certain direction. And we want to control that. And a very, very simple way of doing that is the following. That's what we call photo nudging initially. And the rule there is just a twofold rule. So whenever you have a particle which is looking into a direction where it doesn't see any kind of target, which is the cross here, then you just leave the particle alone and it's not propelling in any kind of way. Whenever the particle looks into a direction where it sees that target, you switch it on and the particle propels actively in a direction which is bringing the particle closer to that target. So this is what you could call photo nudging, but since there's no direct hit of this kind of direction towards the target, you have to define an acceptance angle, which is here the half angle, which is called beta 0. We call that the acceptance angle. In Clement's work, you will find that this is called then the vision cone, for example. And you can define that of different size. There's no problem to that. You can vary that and you will see all the dependencies later. So since the particle is driven by rotational diffusion, you eventually have one event where the particle is propelled and then it's coming closer to a target position, and then eventually it moves to a different orientation where it's not propelled. So you get these kind of stochastic time traces where the green lines show nothing else than the laser illumination, which is switched on during this time, and in the rest of the time it's switched off. And the red line is actually the distance of such a particle from the target position. So in the experiment, this looks like this here. On the left side, we have the target position here. You see the rotational diffusion nicely in the dark field. And whenever it has the right orientation, it will do this kind of jump. And that is here a 1 micrometer particle with an acceptance angle of 45 degrees. so a total opening angle of 90 degrees. So if you want to have a closer look at that kind of problem and the accuracy at which you can control something here, you can devise some theory. First of all, you can describe the stochastic trajectory of these particles with the help of a Langevin equation, in particular an overdamped Langevin equation. So this is this one here, for example, or actually the three ones here which we need overall to describe photon nudging. So the first one is just the one for an active particle. On the left side, you have the velocity of that particle from the overdamped equation. Then you have the propulsion velocity, which can depend here in general on the orientation of the particle in the photon nudging process, multiplied by the orientation of the symmetry axis. And then you have here the diffusion term with the noise, the unit variance noise, the diffusion coefficient. This should be actually the normal diffusion coefficient. This is not the thermodiffusion coefficient. So just my fault here. In our case, for photon nudging, the propulsion velocity or the propulsion speed will depend on the orientation of the particle towards the target. So it will be just a magnitude multiplied with a function h of t, which is telling you either you're propelled or you're not propelled. So the h of t is that green curve you saw earlier. Now I turned it into a blue curve, but it has the same meaning. And in addition to the position, you also have a rotational diffusion, so a reorientational motion, which is driven by thermal fluctuations. And this is the rotational diffusion coefficient dr here, which enters this kind of equation. And you have some kind of noise, and this is here expressed in the vectorial form. So this is a vectorial noise in principle, well, which it is here as well. Okay, so this will give you trajectories for a single particle over time, and you can do your calculations with the help of that. But if you are more interested in average properties, then you're more interested in the probability density. So what's the accuracy of the localization here is one of the questions you may ask, and then you would like to know the probability density distribution to find the particle at a certain distance here from that target position. And that is, of course, given by the Fokker-Planck equation, or in the more simpler case by the Smoluchowski equation in the overdamped case. And here you have that, a normal diffusion term and an advective term, which are brought together. So that's essentially it. So if you really want to know something about that, you have to dive into these theories, how to solve that, how to get something out of that. I will try to explain it in a more simpler way based on some arguments you can easily find. So before I do that, I would like to point you also to the notebook, which is also mentioned in the lecture notes to my lectures. So you either find it in the lecture notes or on the GitHub website, and there you have a whole notebook in Python, which allows you to simulate active particle motion and also photon nudging processes, and even some of the applications I will show later, for example, the binding of dimers and things like that. And here you see the simulated trajectory, where you see clearly that there's a higher probability to find the particle close to the density, and we'll later calculate the variance of that and take the square root out of that. So rho is the distance from that target, and that gives us the localization accuracy. And here you have a plot of the mean square displacement, where you see that's essentially diffusive until it hits the boundary. So it's confined. It looks like the mean square displacement of a particle which is confined in an optical tweezer, for example. But of course it's not. There's no tweezer potential available here. So how can we understand now this kind of photon nudging procedure and what's going on there in detail? And we take two steps. So the first step shall assume that we have an infinite time resolution of our setup. So we can take images very, very quickly. So there's essentially no delay between the individual images, or no time between the individual images. And so this will be the first one. So overall, photon nudging towards a single target position corresponds to the situation where particles drift towards the target and get localized there. So overall, you have a two-dimensional drift field here, which is given by a radial drift velocity v of rho. Rho is the radial coordinate here, which will drive your particles or the individual particles somewhere there. On the other side, when you have localized your particle, there's a drift which should happen due to the fact that you have a high concentration there. So there's a diffusive current which works against the drift current with the velocity. So if this is the target, this is the radial coordinate, you have the diffusive drift current going in the radial direction and the nudging current which is going towards the target, so in the negative radial direction. And in a steady state, both currents should sum up to 0. So at the end, the solution will give you the probability density distribution P here as a function of rho, finally. So the question is now, what's the V of rho? And it turns out that the V of rho in general can be written as the propulsion velocity of your particle, which actually points along the symmetry axis, multiplied by these two coefficients, and one is the average duty fraction and the other one is the average geometric factor. They have some simple meanings. The average duty fraction is the time, the average time essentially the particle spends in the on time divided by the total time of on and off. So if you assume that this particle here, for example, with the edge of its acceptance angle is just switched on, then the particle will do rotational diffusion and that target will move here in and out again. And one on time is finished after the target moves out of that acceptance angle again. So this is a first passage time problem, as it is called. And whenever such a period ends, you can determine the length and you can do then many of them. You will get an average on time from that, which is entering this coefficient. In the same way, you can also have an average off time coefficient when the target is outside until the particle really hits with its boundary of the acceptance angle, that kind of edge again here. So there's a mean on and a mean off time, which both come from statistical considerations of these mean first passage times, which can be calculated. And what you finally get is that the average duty fraction, this FT coefficient, is the acceptance angle divided by P, right? So if it's just pi, it's essentially always on. So the other thing is a geometric factor, and geometric factor has something to do with the component of the velocity towards the target. So if you see here again this kind of situation where the particle would be switched on, then it actually propels in that direction. So it has only a component along the radial direction towards the target. And therefore you have this kind of average geometric factor, which is the sine of beta 0 divided by beta 0. So both go in and limit this kind of velocity in a certain way. So for the moment, we'll assume that despite of these factors, this speed towards the target will be constant. It will not depend on any kind of distance here. And then you can easily solve this kind of equation here, diffusive current plus nudging current equals to 0, to get the steady state distribution. And if you try to solve that, it's pretty easy and straightforward because that's a problem you already know. It's actually a sedimentation problem. So in a sedimentation problem, you would have particles which are sinking down to the ground with a constant velocity, and they would enrich in concentration at the ground. But of course, there's also diffusion and concentration gradients which form then and which would drive them up again. So you have a balance of diffusive current and advective current, which we have, of course. The only difference is that we don't have a planar ground. We have just a singular point in the middle, a target to which this all happens. So the distribution really looks like this here. It's the velocity squared as divided by the diffusion coefficient squared multiplied by this exponential function, where you have here the distance rho from the center, and you have the velocity and the diffusion coefficient. So this kind of quantity here, diffusion coefficient divided by the velocity, is nothing else than a length it's the so-called sedimentation length, and it's the characteristic extent of that exponential probability distribution, which you see here for different velocities. So what you recognize is that for a low velocity, this is quite extended, and if you increase the velocity, it gets more and more localized, and according to their theory, if v goes to infinity, actually you localize that completely at that point, right? So that directly means that your localization accuracy, so the control accuracy you have in terms of localizing that at a special point here, is going with the square root out of the variance of this kind of formula, and it essentially gives you the sedimentation length but multiplied with the square root of 6. Yeah. Okay, so there is one thing to see. This is the kind of sedimentation problem which will come over and over again in my talk, I think, and that for infinite time resolution you would actually have a perfect localization at a point. Unfortunately, that perfect or that infinite time resolution doesn't really exist. You always have a finite time resolution. And with finite time resolution, I mean here you take an image and that it takes an exposure time, and then you take another image with a certain exposure time, and they follow on top of each other with a certain inverse frame rate, right? So before you apply the next action, because you get some new information, you always have to wait a certain moment, delta t, which is bigger than 0. And that has now the following consequences. The main consequence is that the photon nudging field, this velocity field, is not anymore of constant speed everywhere, but you have a distant dependent speed. So usually you would have a situation like this here. This is the edge of the acceptance angle. The particle would propel in that direction. It would propel for a time delta t before you do it again. So we'll move a certain distance delta r, and that brings the particle a certain distance delta rho actually closer. So the delta r and or the delta rho, actually I should call it delta rho, is negative because you approach the target. So, but there's also the other situation which is depicted here. So if you're really close to the target position, then you move during a time a certain distance, again the same distance as here, but you on average move away from the target because your delta rho here in that case is positive, right? So that means the velocity field or the speed approaching the target depends on the distance from the target. On the outside, the speed goes inwards, but if you're close to the target, it goes outwards. And there's in between a region where the radial speed here is actually 0, and there's some kind of critical distance where the particle has only tangential components and no radial component of the velocity anymore. So that can be easily calculated. It's just the propulsion velocity times the time resolution of your setup divided by 2 times the cosine of this opening angle. So apparently, and that's not really a surprise, but of course you have to realize that the time resolution of your setup limits the localization accuracy of your feedback loop, or the bandwidth of your feedback loop somehow limits the spatial resolution you can obtain with that kind of thing. So you always introduce an arrow by arrow. So that is also contained in that notebook I provide to you, and you can have a look at the details there. So here's, for example, the result of a simulation where you actually see that. That's the radial velocity as a function of the distance. As you come closer and closer, it goes to 0. Here's the RC, and then it grows. But of course, the simulation did not have too many time points. You get some statistical fluctuations here in that case. Okay, so you can bring that overall all together into a more complicated theory, and that uses 2 kinds of quantities which are unitless, which are important. One is the revolution number. It's the number of turns you do during your time resolution delta t. We call that lambda. So it's delta t divided by the rotational diffusion time. And the second one is more or less related to the Becquerel number, if you want, as well. So it's the velocity of the particle multiplied with the rotational diffusion time divided by the size. It's the propulsion number, as we call that. And you can measure then all kinds of different combinations of time resolution or velocity and things like that. So here on that axis is the propulsion number or the log of that. Here's the revolution number, and in the y direction or in the z direction, it's in that contour plot actually the log of the localization accuracy divided by the radius for a specific acceptance angle, poo. Essentially, there are two limits here. On the right side, you see this kind of overshooting limit where you have this stable circle around the target position. On the left side, you have something which is diffusion controlled. So since you don't see that nicely here in that graph what's really going on, so we take just that lambda equals to 1 here, make a cut through that, and look at different point clouds around the target position. So for a low propulsion number for a low speed, so you're in the diffusive limit, you see here essentially a single peak in the middle. It's a bit noisy, but the extent is limited by diffusion. And you can understand that quite easily. Once you've reached the target, you got to cross the target, you go into an off state, your particle reorients towards the target, and while it reorients, it also diffuses away a certain distance. So the localization accuracy there will be given by the diffusion coefficient somehow and the rotational diffusion time, right? Or this will be limited, it will be proportional, not equal to it. So there's somewhere the optimal region, which is here along that line. So if you scale delta t and the velocity accordingly, you can stay always on that line. And then you have the optimal localization, which is much narrower than the left one here. But if you increase the velocity too much, for example, you get this kind of overshooting, and then they have this kind of donut structure. And this is this kind of stable orbit. In principle, the particle rotates then around the target at this critical distance here, RC, which is given by the velocity and the acceptance angle. So you can go through all of that now and try to optimize even the acceptance angle and find the right acceptance angle to get the best localization at the target. And in 2 dimensions, this will correspond to pi third. And the minimum localization accuracy will be given by 6.9 times the radius divided by, multiplied by the square root of lambda. So actually it turns out that the localization gets better if you decrease the size of the particle, which is kind of interesting. So the smaller you get, the more precise you can localize something, which is counterintuitive because you expect that noise and Brownian motion would influence everything. But the fact is actually that this, first of all, only happens along that line. And the second thing is that the process which is doing that is a competition of rotational and translational diffusion. So the translational diffusion coefficient goes with 1 over the size. The rotational diffusion coefficient goes with the volume of the particle, so with r to the power of 3. That means the smaller you make the particle, the faster it reorients into the right direction and gives you a propulsion. And therefore, the rotational diffusion is ensuring that you can localize the particle actually more accurately. This is kind of an interesting outcome of that kind of theoretical consideration. Okay, so there are more questions which you can ask, of course, here. How fast can you go from A to B? How does it depend on the acceptance angle? You all will find that documented in one of the papers. I don't want to do that to show you everything here. So, but importantly, you can go now from here somewhere, and I typically show you that where to go. You, of course, can do that also with multiple particles, not only 4 particles here, as in this case. Here we have 4 particles which are nudged to locations at the sample, which we define. You can have this kind of orientation or position dependent nudging, which we saw and which we'll use in application number 1 later. You can correlate the particle propulsion with other particles. And there are beautiful examples by the Beschinger group, for example, which even control the orientation of that particle actively. And there's also a way to do something more complicated. You can bring swimmers away from surfaces where they have hydrodynamic interactions into the volume with a 3D version of that. And you can study these far from boundaries with the help of a 3D photon nudging version, which is a bit more complicated, right? So these are some very basic ones. You see later in the applications anyway, more complicated stuff. The second thing I wanted to report about is a more advanced control, because we saw now that rotational diffusion is limiting to some extent the accuracy at which we can control at least large particles. So imagine you have a 3 micrometer sized particle and you have to wait for the reorientation by diffusion to happen. This could take a long time, seconds, because the particle is so large, and therefore you want to have control even over the orientation. And actually the symmetric swimmers, which I showed you earlier, allow you for that, and I just try to show you the differences. So these symmetric particles had gold nanoparticles all over the surface, therefore they have intrinsically no structural asymmetry, which you would need to break the time symmetry of the Stokes equation. But you can shine the laser onto one side of the particle and release the heat only on that side, and then you have the same kind of propulsion mechanism that you have also for the Janus particles. It only depends now on the position of your of the laser on the particle, and especially on the displacement of the particle here, delta as we call that, from the center. If you do that just at the center, everything is symmetric, no propulsion. But if you do that on the left, particle will go to the right. If you do that on the right, particle will go to the left. You see here how this depends on this displacement delta as we've measured that, and this is an analytical curve we obtain for that. So there's a complete theory which also describes that, if you want. So in that case, you would now place the laser at the edge of that kind of dark field image, for example, and then the particle would propel, and you do the same kind of laser steering with an acousto-optical deflector. But now there's one big thing: you don't illuminate the whole particle, but you illuminate only the edge, and during your exposure time, the particle slips out of that laser here. And that leads to the fact that the velocity of the particle, or the speed, as a function of power, is not anymore linear, but it depends on the exposure time and has this kind of nonlinear behavior. So it's always good to measure at low powers. You see here, we just focus 0.1 milliwatt to the laser and get easily 10 micrometers per second propulsion velocities here, propulsion speeds here easily. Well, that's what you have to take into account, but of course this can be all evaluated, and here you see again the analytical curves for the description. So we have that under control. So, but overall, the control you obtain by that swimmer is much, much better than for a Janus particle here. You see driving the particle between two target positions, and you can localize them at the target positions and look at the localization accuracy, this error. Again, now it's called rho and not sigma. But this is the curve you gain theoretically, and it consists out of two regions again. One region is diffusion limited sedimentation region, and the other region is again the overshooting here. So it's the same procedures, except the fact that rotational diffusion is not anymore relevant, so it doesn't go into that part of the length scale, and therefore you can localize that with 200 nanometer accuracy, right? It's even like that this particle can be controlled even if it's smaller than 2 micrometers, even if it's 500 nanometers. There's a certain position of the laser which you can use to control the particles in the same way, so you don't really need that. So this kind of particle gives you now the freedom to control almost everything. So the only thing you probably don't control is the translational diffusion coefficient, but you probably can even control that in a way. So what I show you here is that one particle is driven along the edges of a square, but we add to that motion artificial noise. So by adding this artificial noise, you can introduce different rotational diffusion coefficients, for example, but you don't have to change the size of the particle, of course. That makes big advantages for observability, for example. You see here how the excursions to the environment are changed if you add additional noise. And without saying, it's also obvious that you can do that not only on a single particle, but you can do that also on multiple particles, up to 100 particles. And you even can control them within a time range of 50 milliseconds or even faster. It only depends on the processing speed and not too much on the number of particles. Okay, so this is a first look at how you can do feedback control. And from that point, we can readily go into application. I can show you what kind of things you could do, for example, and there are other good examples, very nice examples, of course, by other groups.